now let's talk about if I've got a switch and I've configured this as VLAN 10 and this as VLAN 20. So these ports are in VLAN 10, these ports are in VLAN 20, and guys, I literally go in, there's a command, I'm gonna go interface, whatever, fast Ethernet 0/1, and I'm gonna do switch port, access, VLAN 10. I'm literally gonna type a command on the individual port itself and tell it what VLAN it's gonna be, okay? That's how the switch is going to be divided this way because I went in and entered in all these commands. Everybody follow me? Now, we know how it works from a forwarding and flooding point of view. We've talked about that. We've talked about the spanning tree idea. If I've got multiple switches out here, how that's going to work. But how do I get this PC that's plugged in here to talk to this PC that's plugged into here? We said we gave this guy a 10.2 address, and we gave this guy a 10.3 address.
You would need a router, but you said you could do it a different way.
Right. So my concept is if I take one port and I plug that into a router, well, that router's having a bad day. Then I can get my VLAN 10 traffic or this subnet, so that means this is the 10.2 subnet. And if I want to talk to the VLAN 20, I can take another port and plug it into this, and this could be 10.3. So this is fast Ethernet, let's just say 1/0, and this is fast Ethernet 1/1. So 2 physical ports, 2 physical cables. Everybody all right with that?
Yep. Good.
In that case, I send traffic here. When I go to the destination address, I'm going to see that I'm literally in my IP header, my layer 3 header. I'm going to have my source address, my source IP, which is 10.2.1.5. My destination IP address is going to be 10.3.4.5. And what did we say from this PC? Do I have a subnet mask configured on this PC?
Yeah, it's 255.5.0.0.
Right, I have 255.255.0.0. I'm getting this configuration from DHCP. Remember that. We talked about that a couple weeks ago. I get the IP, I get the subnet mask, I get the default gateway, and I get DNS addresses. Remember that?
Yep.
I get all that, and that's how I configure this PC. This PC takes the subnet mask and says, I only care about the first 16 bits. So if I'm going to a destination that's in a different network based on my subnet mask, when I go to build the layer 2 header on here, I know my source MAC is whatever this is, you know, let's say source MAC address A. I know that. What is my destination MAC? We talked about this last week or the week before. How do I find out what the destination MAC IP address is? What protocol?
ARP.
ARP. I do an ARP request, Address Resolution Protocol. This tells me if I have this IP, then what is the MAC? So I'm mapping IP to MAC. I know the IP, I'm looking for the MAC address because I'm trying to fill out this information. ARP is done as a broadcast. Can a broadcast go across a router?
No.
No. So if this PC sent a broadcast over to this router, would it ever reach this device?
No.
No. So there's no point in doing it. And the PC knows that because of that subnet mask. Remember talking about this?
Yeah.
Okay. So who do I send the ARP to? I send it to this address, the default gateway's IP address. Because when the packet shows up here, if I want to route from one interface to another, if I want to route, the router has to look up the destination network, which is going to be taken from the destination IP address in the layer 3 header. Can I look at the layer 3 header if I still have the layer 2 header on?
No, it's encapsulated.
Can I take off the layer 2 header if it is not my MAC address? If that destination MAC address is to MAC address X, and my destination MAC address, my MAC address, my source MAC address is Y, can I de-encapsulate the packet?
No.
Oh, remember we said it's just like the US mail. It's a felony to open somebody else's mail. So the router will not even take the layer 2 header off to route it if that destination layer 2 MAC address is not the router's MAC address. So I need it to be X that goes into this field. So I send out an ARP to the default gateway, which is the IP address of this interface. The router responds to the ARP back with X. I put X in this header. Now when I send the packet out, it says, oh, that's for me. It takes off the layer 2 header on it, says you're going to 10.3. Let me go over here and look at my routing table. And if I know that destination address 10.3 is out port fast Ethernet 1/1, then I will route it. Everybody remember this?
Yep.
So the router takes off basically your MAC address, adds its MAC address, and then forwards?
Right. So in this direction, if I look at it, it's going to be X as the source, or as the destination, A is my source, right? When I send a new packet out, because this packet has only got a layer 3 header on it, I got to put a new layer 2 header on it. And now that's going to be, if this is Y and this guy is B, then my new layer 2 header is going to be from Y to B. The layer 3 portion of it will stay the same. Everybody following that?
Yeah.
This is the de-encapsulation process. The PC encapsulates it on this side. I put it in. When I go out the other side, I've got to do a new one. This is not sourcing from A now. This is now sourcing from Y going out this direction. Okay? Now, when I do that, remember what we said. If I've got 2 switches plugged together, and I've got VLAN 10, and I've got VLAN 20, and I've got VLAN 10, and I've got VLAN 20, can 20 talk to 20 and 10 talk to 10 without a router?
Unless they're layer 3 switches, no.
No, they're both layer 2 only. So these guys over here are the 10.2 address. These guys are the 10.2 address. These guys are the 10.3 address. These guys are the 10.3 address. Same VLAN.
Yeah, you should. The 10 should be able to talk to each other, and the 20 should be able to talk to each other, but not 10 to 20.
That means that 10 and 20 need to be able to go across this link. Would you agree?
Yeah.
And what did we say? We had to configure this link different, because I can't go take this command and assign it to this port. Because if I assign it to this port and make it VLAN 10, then VLAN 20 can't go across. If I make it VLAN 20, then VLAN 10 can't go across. So what do we call this link in the middle?
Trunk.
Good. See, you're learning stuff. And trunk, we said, you may read in the book, for example, that there was something called ISL, Inter Switch Link. This was a Cisco proprietary, no longer used. The standard after that was 802.1Q. This is what's used on all switches today. So now literally on this port, let's say it's fast Ethernet, whatever, 0/10. I'm going to come down here and do interface, fast Ethernet, 0/10, switch port, trunk, .1Q. Okay, so I'm literally going to type a different command on this port than I do on these other ports. Okay, and by doing that, that means that when I send that layer 2 header out, this area up here, essentially what I'm doing is I'm going to add an identifier in here that puts on the VLAN. Okay, so when I go to send it across this, if I put the 10 header on the packet, when I get on this side, I take off that extra little bit. I know now that I'm going to send it to only ports in 10. Something coming from 20 is going to get the 20 header on it, and when it gets onto this side of the switch, then it's only going to go into 20. Get the idea? You okay with that?
Yeah, I got it.
In this topology here, do I need this link to be a trunk? Think about it for a second. No, because it's only one VLAN going across, right?
Yeah.
But what's the problem with this topology?
You need to have a router set up to communicate.
Okay, I got to have a router. That's fine. I'm talking 2 different subnets. I can do that. What happens if I add VLAN 30 on this switch? What do I have to do now?
You need another route, or no?
You need to set up another link between the
Need
routers.
to set up a trunk port.
Right, I need to burn another port on the router and another port on the switch. So if I've got 400 VLANs on this switch, that means I need 400 ports on my router. And I'm using 400 ports on my switch just to connect to the router. Think maybe that's not quite as efficient as we could be?
Yeah, not at all.
Okay, so what we did is initially we came out with the concept of, anybody know what I'm about to draw? Because I have put this term on the board before.
I have no idea.
I'm going to redraw this. So VLAN 10, VLAN 20, but now it's got one interface. Okay, so this is fast Ethernet 0/0, and we'll just say it's 0/0 on this side, and on the router it's 0/0 as well. One interface. I know I can make this a trunk, so I could get 10 and 20 to go across it, right? So I can have 10 and 20 go across, because I know that's what the trunk will allow me to do. But on the router side, where is my 10.2 interface and where is my 10.3 interface?
They're on the same port.
If they're in the same port, can the router, can I take a router over here and have one interface out and give it an IP address of 10.2.1.3 and an interface of 10.3.4.6? Can I do that? What do you think?
Yes.
Yes.
Guessing yes, because this is what the example's about.
The router's job is to separate networks, right? To route between networks.
Yep.
How can I have 2 networks out of one port?
Are they virtual?
Gigabit gateway.
So what I'm going to do is I need to be able to say yes and no at the same time. So what I do is I essentially do it like this. So I'm going to now take this one physical interface on this router. This is one cable. And I'm going to make this fast Ethernet 0/0.1. And this is fast Ethernet 0/0.2. This .1 and .2 we call a sub interface. From the router's point of view, it treats it just like it's a separate cable. Okay? So from the logical point of view, if I've got 400 VLANs, I can have 400 sub interfaces, but I only have one cable. You get the idea?
Yeah.
So from the switches side, I'm configuring it as a trunk. On the router side, it's configured as a trunk, but each one of these is, this is a 10.2 interface, this is a 10.3 interface. So from the router's point of view, I still have to route between these interfaces just like I would if I had two physical interfaces. Right? So that was our first way, is to create this sub interface, which is a logical interface. It's not a physical interface, it's logical. One physical means multiple logical. Okay? We use this concept in a lot of different things. We used it here in VLANs, but in all actuality, it had already been invented long before that. We used it in WAN topologies because we had the same kind of topology in frame relay, where we have one connection to our WAN topology, but we have multiple branches sitting out here. So we had already came up with this concept of sub interfaces. They just adapted it on Ethernet. Okay? We call this mentality a router on a stick. You will see that again. And that's the idea where I only have to burn one physical interface, but I can still have as many logical interfaces as I need, so that every logical interface is a different VLAN, so that when I'm sending the traffic back from the router this way, I make sure in that 802.1q header, I'm adding the VLAN identifier. So if this shows up in 10, when it shows up over here, then I know I need to send the traffic that way. If it shows up with the 20 header, then I know I need to send it this way. Okay?
Now, what's the
So traffic will come in
practicality
10.2, literally from A to X. I'll do an arc that way. I'll route. I'll do another arc this way so that I can go from Y to B. So I still take the layer 2 header off, I route it, and then I send it back out with a new layer 2 header on it, even though that's all coming through the same physical interface. So everything I described with the physical interfaces is still functionally happening on the routing, but now I just did it in a logical way so I didn't have to burn up more interfaces. Get the idea?
Yeah.
Yep.
Did I lose anybody? I'm pretty sure I got
I do have a
Casey
question.
and Sydney. What about everybody else?
I do have a question. What is
Go
the
for it.
practicality on the trunk? You know, can you literally have all 400 going on one cable
Yep.
and it's not going to block traffic?
I don't know. What do you mean by block traffic?
Like, it's just going to overload that one cable.
So you're saying there might be a speed problem
It
here?
just slow it down.
We have a bandwidth problem.
So you're saying that if I have every one of these is a 1 gigabit link, and this is a single 1 gigabit link, which right now I'm saying is a 100 meg link when I'm doing this fast Ethernet.
Right.
If it was gigabit, this wouldn't be FA, it would be a G. But you're saying if I have 48 ports all configured at 1 gigabit, and I'm using one single gigabit link to do all these sub interfaces, I might have a 40-to-1 oversubscription, and that could be a problem?
Right.
Absolutely. So why not just put a 10 gig interface on the router and do that? Guys, the reality is we still have very few routers that have 10 gigabit interfaces on them today. So this has always been an oversubscription problem. And I absolutely love the fact that that pops up in your head. So let me tell you how we fixed it. The reality is we don't do that router on a stick topology anywhere anymore. We don't have a physical router sitting out there like that. So what we end up having is, let's say we have a very large switch like a Catalyst 6809, which means that this card, this chassis, has 9 slots. 1, 2, 3, 4, 5, etc., etc. Now, in this slot, I may put 2 supervisors. They won't necessarily be in slot 1 and 2, but just get the concept for right now. So these supervisors are like my motherboards. This is where my CPU, this is where my memory, this is where my route processor is, and this is where my switch processor is. Okay? So the router and the switch is literally on the supervisor. And then these are all line cards. So it may be a 48-port line card, it may be a 10-port line card, et cetera, like that. So what I end up doing is on these line cards, let's say that these ports are VLAN 10, and let's say these ports are VLAN 20. Okay? Because this is what we call a layer 3 switch, it means that I'm going to route and I'm going to switch. Okay? Now, these cards functionally together, if you look at them, if I give you a sideways view of the chassis, I'm going to take a line, one of these cards, whether it's a supervisor or a line card. Literally, these things can be like 25 pounds or more. They got all kinds of ASICs sitting on them and all that. I slide them into a chassis. That chassis has connectors on it, which match the connectors on the back of the cards. Okay?
Mm-hmm.
This chassis basically has a way so that these cards can communicate with each other back and forth. We call this a backplane.
Breadbasket. Backplane. We called it the breadbasket. Backplane and breadbasket at the same time.
Yeah, I never heard it. I wouldn't use the term breadbasket anywhere else. It's not really a common term out here. I know what you're talking about, but not necessarily in the switching world where you hear that. You'll basically hear this only referred to as the backplane, or maybe somebody that's really technical may call it a control plane, because then they're going to be talking about the difference of traffic that goes across the backplane versus data that goes across a data plane. And we may call it out in 2 different places like that. But typically in the switching world, we're going to refer to this as a backplane. And basically, this has got a speed itself because these connections have a speed. On the 6809, these may be 40 gig connections, and I may have 2 of them per card. So instead of having to be limited by that 1 gigabit link, I now may have, even at the time when this first started, which was roughly about a 6500 chassis, and when that chassis came out, it had a 40 gigabit backplane. Today we're in the terabits on most of our switches that are like this. Okay?
So they're just blowing it so far out of a proportion that it will never matter.
Yeah, as long as even when I had the 40 gig backplane, if I had a card that had basically it's a 1 to 1.2 over subscription, if I didn't use 8 of these ports, it didn't matter if I have 40 ports of traffic coming in. As long as I had that 40 gig connection, I had the 1-to-1. You see what I mean? So by literally the router on the 6 topology is still here. I got VLANs over here. I got VLANs over here. I got a router up here. I'm going in blue. I'm coming out red. You know, that type of thing. So the router on the stick concept is still here, but now I'm doing it on the chassis itself. So I got rid of that bandwidth over subscription that I'd have to have on a single link. Also, what's the odds of that one physical cable connecting that switch to that router of going down? My odds of a backplane going down are almost impossible. I literally, in 20 years, I think I've seen 3 scenarios in my 20 years where there was a backplane problem. And honestly, that was just because the engineer jammed the freaking card in too damn fast, and he bent a pin. And it just made the chassis go screwy. Not something that normally breaks because it's not something that moves. Once you slide the card in, you fasten it in, you probably never take the card out ever. Okay? So this multi-layer switch, this layer switch kind of concept is how we do it today. And even in a lot of ways, I don't even have to go up that high because I've even got this route processor to the point now in a lot of switches where that route processor functionality is down here on the card. So literally I go red here, out blue there, and I don't even have to go across the backplane. So we've gotten very, very efficient at this point. So the concept was good, but now it's more likely to do my inner VLAN routing on the same chassis where the VLANs are defined. Get the idea?
Perfect.
Okay. So just mixing a little bit of the concept, you will be tested at the CCNA level about router on the stick, about sub interfaces. The reality in the real world, I'm not going to do that crap anymore. I don't need to do it. I don't do sub interfaces on here. On this particular router, if I blow it out up here, it doesn't have sub interfaces. It has interface VLAN 10, and you put an IP address on it. Interface VLAN 20, and I put an IP address on it. I'm still doing logical interfaces, but I just go ahead and label them as VLAN 10 and VLAN 20. Literally, they don't exist until I type, I go into configure terminal and then I do interface VLAN 10. When I hit return, boom, it suddenly exists. When I go and do show interface, it'll show up just like it's a physical port. Okay, which is the same concept behind the sub interface. That's the same way a normal router would work. But because I'm doing this specifically for VLANs here, that's what we do today. We don't do sub interfaces, we do interface VLANs. And that's how I put a layer 3 address on it, and that's how it's defined out that way. And then that's how I do my inner VLAN routing on the device itself. You okay with this stuff?
Good.
So,
All right, so like I said, what I'll try to do this week is go ahead and build out like some basic topologies. We'll start with the router on the stick thing, and then next week when we come in, we'll kind of build a layer 2 topology. We'll go in and look at some of the spanning tree commands. Then we'll overlay on top of that some of these the VLAN commands to go between. So we add in the routing and the switching. So we'll do some of that configuration so you guys can see the concept now deployed. And then I'll even use, I may even use some links on a layer 3 switch. I'll have to see. I think I could do that on the models that software lets me draw on. If I can do that, then I'll even go back at this point and show you the inner VLAN so you can see some of the configuration that goes with this. Okay. What I want to spend maybe 20 more minutes on is, like I said, guys, from a root point of view in the class, I need you to understand the concepts of VLANs, spanning tree, and the router on a stick idea. This is what you're going to be tested on. So this is the exam. So there's a bit in the book and some other things I need you to go through and memorize so that you can pass the certification. Understanding this stuff makes you relevant during the interview, okay? Because we don't do this anymore. We do this now, okay? What I want to show you now, though, is likely the companies that you're going to go in and talk to, They've been doing this for 10 years. They don't need help with this. You're not going to come in and say, oh, I understand how this works. You're going to go, oh, great, we really need somebody on the team that gets that. They're going to go, so what? We got a lot of people on the team. If you come in just with this, they're going to go, yeah, I don't even know if you understand enough about my environment. Okay? If you say this, at least you understand kind of how it works, but probably what they're dealing with, you know, the new stuff, the stuff that's changing, I want to go over that a little bit now. Okay, so you don't need to memorize it. You can just kind of listen so that you can see some of the more modern stuff that we're having to deal with, the bigger challenges like in data center and things like this that we're having to come across. Okay, everybody okay with that? So what I'm about to talk about is really kind of taking you a little, it's a glimpse into a lot deeper. Everybody ready?
Okay. Yeah.
Let's do it.
So, first off, let's assume that I have a data center. Okay, that data center has lots and lots and lots and lots and lots and lots and lots of switches. To give you an idea, the last data center I built with Lehman Brothers, I think we had upwards of about 565 9-slot, so 6509s. That was basically giving me about 500 ports per switch. Okay. And if you look at in the data center, every one of these ports is a server. Okay, so inside a single building, you got a lot of servers there, a lot of switching infrastructure. Now, if I'm a company and I got one data center, do I have a fundamental problem with my design? From what we've learned so far, from a network engineering point of view, is it ever good to have one of anything?
No. 2 is 1 and 1 is none.
No.
No.
I'm always looking for a single point of failure. Single points of failure mean the company's done. So I've got 2 access switches. I've got 2 distribution switches. I got 2 core switches. But what about the data center itself?
If there's a fire, you're done.
Literally, guys, let me just give you a little glimpse into data centers. Since this is something we're going to, you know, as you guys track through the apprenticeship program, as you get through, we're going to go, you know, all of you are going to get a little bit of data center. Some of you may choose the second half of the program to kind of specialize in data center instead of wireless or security. Those you'll go in really deep. So let me just give you a little glimpse on kind of what some of that looks like, because that's what makes you relevant out there today. If I look at a data center, first off, if I start at the server, I'm probably going to have 2 production ports. So I'm going to have 2 cables, 2 NICs on every server. In case I lose one, I got the other one. Okay? Now from a Microsoft Linux point of view, I'm going to do things like NIC teaming and all this stuff to try to keep these things where if one fails, I got the other one, or I may decide to bundle them together and use them both at the same time. I probably also have 2 storage links because, hey, it's a server. What happens if the server goes down and all the data? You know, most modern companies out there today have to keep copies of all your emails for like 7 years. It's a law. It's a regulation. So I'm going to have storage devices over here, which are just rows and rows and rows and rows of hard drives. And I store all that stuff over here so that I can get access to it. Okay. I probably also have 2 connections for what we call out-of-band management or lights out management. That means if for some reason this network over here goes down, then I at least have a backdoor into the server, so I can still configure this server and maybe get it back up. Okay. If I telnet into a device, Normally I telnet in from the production, but what if production goes down? I want to be able to come in from the back door as well. Okay? So very common for my server to have 6 to 10 ports on it. Okay? Not like your laptop where you got one. Okay? So that's at the server level. Now that means I've got all these are switches. Now it happens that most of these are Ethernet switches. These may be Ethernet, or they may be fiber channel, or they may be fiber channel over Ethernet. Okay, so that's a different area. We won't necessarily go into that. So when I come into these two switches, you know, then I got my distribution, my core, and all this model going up. Okay. From a floor point, if I'm looking at a floor plan, basically the way this works, it's going to be cabinets. These cabinets are in rows. If I look inside one of these cabinets, all networking cabinets are the exact same height. They're the exact same width. They're exact same depth. Because all the vendors make their cards and switches and servers all the same exact size, so they fit in a standard cabinet. Okay? So if I look in that cabinet, most of these devices, I'm also going to have redundant power. Because what happens if I lose this power? Do I want to lose my server?
Hell no.
Right? So I want to have redundant power supplies. Well, is that just enough? What if I lose this power company? Do I want to have a separate power company over here? So I don't want to just, if the plug goes out, which is the power supply, I don't just want to have redundancy of that. I may want to have redundant power companies. Everybody following me?
Yeah.
Even in that, I probably want to have one power company coming in this side of the building and one power company coming in this side of the building. Why? Because I want to have backhoe redundancy. So when some Nimrod digs up the ground over here and kills this cable, I don't want him to kill both of my power company cables at the same time. You got me? So usually there's a manhole on this side of the building and a manhole on this side of the building. Okay? When I'm looking at servers and switches and where I put them, do I put them at the end of the rows, or do I put all the switching infrastructure in one spot in the data center floor? Different models behind this. Okay? Where do I put my servers? If I have an application that needs 20 servers, do I put them all in the same cabinet? Do I put them all in the same place? Or do I try to put one over here and one over here? Because what about the fire sprinklers that are here? What if one of those goes off? And it basically puts, you know, water and electricity generally don't mix, just so you know. So if that sprinkler head goes nuts and it kills this whole area, did I just take down a portion of my company, or do I want to spread my servers out across the data center? Everybody with me?
Yep.
Redundancy upon redundancy upon redundancy. We are looking everywhere for a single point of failure. Even with the switch that I'm describing, and get rid of some of this, just so you guys get a little glimpse. I just want you to see that, yeah, we actually go quite ridiculous on some of this stuff. Even on that switch that I drew a minute ago that had the slots, and I look at a line card down here, that line card's got ASICs on it. So maybe these 4 ports are plugged into that ASIC, these 4 ports are plugged into that ASIC. So when I'm connecting these devices together, and then I have a second connection here, do I put them both here? Or do I put one here and one here? So even I have ASIC redundancy. Or do I do one off of this ASIC and one off of this ASIC on 2 different cards, so I have line card redundancy? You guys see how far you can go with this?
Yeah.
Okay.
Sounds very interesting.
So in a modern data center design, I have to worry about all of that because, guys, that little 1,500 byte packet has got a whole lot of freaking money packed inside it. The company can go bankrupt in a couple hours if they're dependent on the network to do certain things, okay? So when I'm looking at, if I've got all that redundancy inside the data center, do you not think that I want to have 2 data centers? So I want to turn around and do it all the way across like this. So a lot of technology that's went into this is that if I have a server over here, and this server is running application A, I probably want to have a secondary server to do that same function with application A if application A is a revenue-based application. Would you agree?
Absolutely.
Agreed.
So do I put that secondary server here, or do I put it over here?
Oh, you put it in the second one, in the redundant data center.
So it would seem really intuitive that, oh, why wouldn't you do that? There's a whole lot of problems with doing that. Let's say that this is in Atlanta and this is in San Francisco. Okay? Now, if I'm going to have this server be plugged into this infrastructure, and if this server goes down, I want this server to be the backup that's plugged into this infrastructure, then I've got a whole lot of things I need to think about. One, let's say that this entire network is the 10.2 network and it's split into a lot of subnets. Well, likely this one was split into 10.3 network. So if this server goes down, how does this server take it up if it's a different address altogether? Because remember, at the end of the day, it's always a client to server communication. If I set up a session between these devices and then I change this device to the backup and this device has a different IP address, it breaks my session and I got to reestablish it. So no matter what, I feel the pain. You get what I'm saying?
Yeah.
Now, what happened in the server market is we figured out a way to take these servers and basically make these into virtual machines. So there's a physical box, all right, that's hardware, and then I'm making the server basically a logical instance. Now I have the ability over here on this physical box to move this guy over here. So if I have a physical failure with the hardware, I can shift it across to this side. VMware is usually what we're using, and we call this vMotion. Okay? It gives me a way to virtually shift that server over to this side. Now, if I'm going to do that, and the server has also got a storage connection, and I've got storage over here, I've got to make sure that I have, you know, some sort of logical shift of the storage footprint as well, because this server in a virtual machine, it's literally a file that is like kilobytes in size. It's just a file with pointers in it. Point here for that, point here for that, point here for that, point here for that. So if that file is pointing to this storage, then I need to make sure if I shift it over here, is it going to point to this storage or do I have to point it to a new storage now? And guys, all this is literally distance based. So I have certain distance limitations on how much I can do. Likely between Atlanta and San Francisco, I can't do this. You know, Atlanta to Birmingham, Alabama, maybe. Because I've got some speed of light challenges I got to deal with because I have a minimum latency in order to get the synchronization between the storage and the server. So from that side, I got a lot of different problems pointing out of here. Up here on this side, I would have a lot of stuff to do this. Now, how do I move that virtual machine between buildings? I need to be able to have some layer 2 network that's tied in between these two buildings. Now, just based off of what we've talked about today, do you really think that all these hundreds of switches in 2 separate buildings should all be one single layer 2 broadcast domain?
That's a terrible idea.
Probably not a good idea because I get one spanning tree instance and the whole freaking thing shuts down. If I get one broadcast thing that goes out of control, I shut everything down. But you can see where I need this layer 2 to move across this stuff like vMotion or what servers refer to as clustering. I need to have that layer 2 simple communication go back and forth. So we had to design some things that allow me to have layer 2, but make sure it was a safe layer 2. So there's a couple technologies. One is called OTV. One is called Lisp. Then we have a newer one that's called VLAN. And these concepts all share one thing in common. I could take a VLAN base of traffic and allow it to logically live all the way through this network. Now the reality is the layer 2 domain stops here, the layer 2 domain stops here. Everything across here is all going to be layer 3, layer 3, layer 3, layer 3, layer 3. So it's literally like I am doing Ethernet over IP. So I'm taking that normal layer 3 header, my normal layer 2 header, and then I'm putting an overlay on that for things like OTV and Lisp. And I'm putting a VLAN identifier in here. So I don't let this be trunking. I don't make it a large layer 2, but I let it go all the way through the network so that I literally could do an ARP from here to here, because I'm wrapping that ARP in like a layer 3 header. Okay? So we've got a lot of things that we can do with that. There's